One of the important points about Prolog is that there are things that we should not do. So a key question is, should we discuss how not to do it? Because if we discuss it, then we may remember these things and then accidentally do them. Whereas otherwise, if we don't know them, we also can't use them. Still, we need to be aware, at least to some extent, of what not to do. Because we need to be able to tell, for example, if what we see is good Prolog code or bad code. So, first of all, why is it even possible to write Prolog code in a way we should not do it? Well, Prolog is a programming language with a long tradition. It started about 50 years ago and even longer ago if we also count its predecessors. And importantly, Prolog is under ongoing development and it will be under development also far into the future. And 50 years is nothing for this. It will take much longer. And as part of this development, new constructs and features are often found and added. For instance, constraints such as div, CLBZ constraints and so on. Meta predicates like if underscore, t-filter and so on. Or also alternative search strategies such as SLG resolution and so on. And such new constructs let us replace old constructs so that we benefit from declarative properties or from more convenience or from greater efficiency and so on. So an important point here is that a few old constructs are now no longer needed because they are superseded by newer and better features. But for backwards compatibility with older programs, the old constructs are also still part of Prolog. And sometimes we can even implement better constructs in terms of these old constructs, at least until the better constructs become available as dedicated virtual machine instructions or as built-ins. But as a general rule, the superseded constructs are of course best avoided in regular programs. So, how do we not do it? Well, one thing we definitely try to avoid is called incompleteness. Incompleteness in the sense that a program fails to report solutions. And it's one thing if the program is incomplete because it doesn't terminate. That's in a sense okay. And a different execution strategy may have better termination properties and be complete. But it's an entirely different thing if the program explicitly tells us there are no or no more solutions when in fact there are more solutions. That's of course extremely problematic because it's incorrect. And there are a few constructs that make our programs incomplete in this latter sense, that is incorrect. For instance, this predicate exclamation mark, also called cut, prevents, among other things, the consideration of alternative clauses. So for example, suppose we have a predicate P and we say P holds for the atom A if exclamation mark holds, and P also and unconditionally holds for B, okay? Then when we query, does P hold for A? Yes, as intended. And does P also hold for B? Yes, also as intended. And now we generalize the query and ask, for which terms X does P hold in general? Then we get A as the only solution. And that's clearly incomplete because we already know that B is a solution too. So in a sense, the predicate has forgotten to mention that there is an alternative, since the solution X is B is incorrectly omitted. Now, one may of course wonder, is this bad? Yes, because important logical properties are now destroyed. First, commutativity of conjunction. If you post the constraint X is B before P of X, it yields a solution because it then succeeds. Whereas if you post the constraint X is B after P of X, that is, we exchange the goals, then it fails. And it also destroys monotonicity, a very closely related property, because the specialization we obtain by adding a constraint X is B, and then we simply state what we stated above, that is, we simply repeat what we said, but we've now added a constraint, and remember that the query above failed, and we've now added a further constraint, so we expect it, in a sense, to fail all the more. But no, if we add this constraint, it succeeds. And this is very troubling because it prevents, among other things, alternative execution strategies, such as, for example, iterative deepening, which only works for monotonic code, that is, if these properties are preserved. And that's only due to this predicate, exclamation mark, otherwise it would work. And I mention this because people sometimes blame other predicates even when they don't destroy these properties. Specifically, this is not the problem of the predicate comma, that is of conjunction. Because one could come to the incorrect conclusion here that comma does not denote conjunction, but it does. It's only that exclamation mark destroys these properties. And yes, this is bad, because the ability to apply different execution strategies is an important attraction of Prolog. Now, one may quickly dismiss this because truly, who has ever heard of a different execution strategy for Prolog, right? That is something other than depth-first search. Well, as mentioned, we can only apply different execution strategies if we retain these properties. And as long as there's so much Prolog code around that destroys them, we also won't hear much about alternative search strategies. But it's our goal, of course, to enable them. So cut prevents consideration of alternative clauses and therefore limits us to one specific search strategy. Another construct that causes incompleteness is if-then. It commits to the first solution, if any, of the if part. And therefore, it's only sound if the condition is ground. For instance, let's define a meta predicate include, where the first argument is a partial goal that holds for all elements of a list which are included. So if the list is empty, then no elements are included, no matter the goal. And for lists with at least one element, it depends on whether the partial goal holds for the element. So in this case, the relation holds if, and now it depends. If the partial goal holds for the first element L0, then the element should be included. So we relate the original list to a list ls, which contains L0 as its first element, and also has a tail t's. And otherwise, the element is not included. So we're making a case distinction on whether the goal holds for the first element of the list. And the remainder of the list, ls0, is in this same relation with the tail of the list with the included elements, okay? And at first, this may appear to work as intended. For example, let's ask, what are all elements greater than 3 in this list of integers? And we call the list of included elements i's. Well, this is the unique solution, and it's correct. So from a quick test, it appears to work correctly. However, what if we take this very same query and instead of 11, we generalize this element to any term x? Because that's a unique attraction of Prolog. We can generalize our queries and ask, what about any such cases? And if we do this, we get an instantiation error, which is an okay answer. This only means that the Prolog system doesn't have enough information to make a statement one way or the other, because there are cases where x is greater than 3 and then would be included, and also cases where x should not be included. And the instantiation error means that to decide this, an instantiation is expected. Now, we could of course use a more general predicate, more general in the sense that it also works for variables. For instance, let's use the CLBZ constraint less than here, okay? And now we get this answer, which is incomplete. Because what if x is less than 4? Clearly, if x is less than 4, then it must not be included. However, the Prolog system has simply omitted this case and instead constrained x to be greater than 3. And that's a huge problem because we've now lost solutions. In fact, even infinitely many. And of course, there's a solution for this because we can simply use t-filter from library rave and ask, what are the integers greater than 3 in this list? So we're now simply using the library predicate t-filter instead of our own definition of include. And now we get a disjunction. This is the first possibility. X is smaller than 4. And in that case, it's not included in the list i's. And second, x is greater than 3. And in that case, it's included in i's. So all possible cases are now accounted for, and nothing is omitted. And that's of course nice, and this is what we expect from a logic program, to truthfully and completely answer what holds and what not. So if-then is another example that violates this. And as a declarative replacement for if-then, we can use if underscore from library rave, and for meta predicates such as the mentioned include and also exclude, which are often defined in terms of if-then and therefore also incomplete, we can use the mentioned t-filter. Another example that destroys completeness and therefore monotonicity is this predicate, \+, which can be read as not provable at this moment. So this is not negation as we know it from logic, where we'd read it as something does not hold, but it refers to provability at this particular point in time. So this introduces a very procedural notion into the program and again makes the meaning depend on a specific execution strategy. For instance, we can ask, is it not provable at the moment that equals of A and hello holds? And we get yes, that's not provable. However, if we pose a generalization of this query, namely, is it not provable that equals of X and hello holds? Then we get no, that's not provable at this point in time. Clearly, because there is a solution where X is actually equal to hello. And that's incomplete, because there are solutions, such as the atoms A, B, C, and of course also other terms, such as every integer and every compound term, where X is really not the same as hello. And if this not provable predicate were complete, then it would have to enumerate all such cases. And it also depends on the execution strategy, because if we add a suitable constraint before the goal, then it succeeds. Whereas if we add it after the goal, it still fails. So not provable is incomplete, as are also other predicates such as not unifiable, which can be expressed in terms of not provable. And also here, there are good declarative alternatives, often also with a long history. For example, instead of not unifiable, simply use diff to express that two terms are different. And this predicate has a very long tradition. It was already available in the very first Prolog system, Prolog 0. Find all is another example. It's easy to see that find all is problematic because it can be used to express other incomplete predicates, such as not provable at this moment or checks for instantiation. For instance, if it weren't already available, we could define var, which holds if the argument is a variable, in terms of find all. For example, like this. And var clearly violates commutativity and therefore prevents alternative execution strategies. And also type tests, such as integer, atom, and so on. These are all incomplete. For instance, are there any integers x will fail, whereas if we add a constraint, it will succeed. So these type tests are clearly problematic, and for correctness, we use the SI family of predicates instead. And incompleteness is maybe the most common mistake in Prolog programs. Maybe because people don't consider it as a problem, or also because they are confused about the direction of consequences. Because if we avoid such predicates, then we can reason very logically about Prolog code and also run it with different execution strategies. So it's not that Prolog can't be run with alternative execution strategies and therefore we can use these predicates. Rather, the direction of consequences, if we are using these predicates, then we can't apply alternative execution strategies. So let's consider an example. Let's relate an integer n to its factorial. So the relation n factorial holds for if the integer is 0, then its factorial is 1. So in that case, we don't have to consider anything else, right? And indeed, we can find such code in actual practice. And we already know now that the result will be an incomplete program. But still, let's think about it. What else do we know about this relation? Well, what about n in general and its factorial f? And we've already covered the case n equals 0. So let's now define the relation for n greater than 0. Well, in that case, if n1 is n minus 1 and the factorial of n1 is f1, then the factorial f of n is n times f1, right? And that's it. And we can use this predicate to compute the factorial of an integer. So this mode of usage or this direction, where the first argument is instantiated, works as intended. However, if we generalize this argument and ask which solutions are there in general, then we get only one solution. So the predicate is incomplete because we've used exclamation mark. And other modes also have this problem. For instance, if we instead of f ask for 1 here, we get n is 0 as the only solution. And that's incomplete too, because what about the other solution? N is 1. So we clearly see from this example that cut forfeits the power of Prolog. Because the prime attractions of Prolog are precisely that we can generalize our programs and queries and reason about them in different ways and run them with different execution strategies. And none of this works if we destroy logical properties such as completeness and monotonicity, and if we cater to only one particular execution strategy by using predicates that only have a procedural reading instead of a declarative one. And we solve this problem by simply removing the cut. And if we now pose the same query as before, we get the same solution as before, and Prolog also tells us that this is the only solution. So the choice point was in fact redundant here, and if we want, we can use z-compare to prevent the redundant choice point. But this is only a matter of performance and doesn't change the meaning of the program in any way, namely the set of solutions it describes. And further, if we again generalize the query and ask which solutions are there for any n and f, then we get this solution as before and also others. So now the predicate enumerates all solutions. So that's nice. And if you focus on just termination by adding false here, so we don't expect any solutions now because of course this can never succeed, but focus only on whether the predicate terminates, then we see that the query doesn't terminate as expected, because there are infinitely many integers for which the relation holds or ought to hold. And if it's complete, then it must not terminate. So it would be a programming mistake if we could observe termination here. Now, what about our other example from before, where instead of f, we ask for all integers whose factorial is 1. We now get 0 as before, and now also 1. And then it doesn't terminate, which is okay. It's not wrong to not terminate. What is wrong, though, is to explicitly say there are no or no more solutions, when in fact there are solutions. But still, it would of course be preferable if this query also did terminate, because we know that there are no other solutions. It's just that with the default execution strategy, Prolog does not derive this. And we can help Prolog to derive this. First, if you think about it, then f can only be greater than 0, right? So we can add this as an additional constraint. And we know that CLB-Z constraints always terminate. And therefore, adding such a constraint can at most improve termination, never by itself cause non-termination. And another thing we can do to cater to the procedural semantics of the default execution strategy is to reorder goals. And we can do this because we are using general predicates. So because we are using predicates that can be read declaratively, such as CLB-Z constraints, we can reorder goals. For instance, we can simply exchange the last two goals, so that the CLB-Z constraint, which we know terminates, is placed before the recursive goal. And with this definition, when we post our query from before and only consider its termination properties, then we see it now terminates. So with these simple changes, we've improved the termination behavior of our program. Of course, termination is not all that matters, and our changes may also have other effects. For example, they may have made the program slower in some cases. But even apart from performance, a huge problem still remains. And it exists in all versions of the program we've seen so far, namely, this predicate is not monotonic. And therefore, it's not amenable to different execution strategies, because it will report wrong answers. For instance, if we ask, is there an integer n such that the factorial of n is 2, then the program tells us, yes, n is 2 is a solution, and no other solutions exist. So according to this answer, n is 2 is the only solution. However, adding a constraint yields a new solution, because if we state that n is the compound term 1 plus 1, so not an integer but a compound term, and then ask, is it the case that n factorial of n and 2 holds? We get, yes, this holds. And n is 1 plus 1 is the only solution. So that's a huge problem, because it means that we can't rely on what the program tells us. Who knows what other solutions there are too? So what we want from a program is, of course, the truth about the situation. If the program tells us there are no other solutions, then there shouldn't be any other solutions. Especially not if we add additional constraints, which should only be able to remove solutions, certainly not add them. And this issue arises here due to the defaultiness of CLBZ expressions, because declaratively a variable in an arithmetic constraint stands for any CLBZ expression, not just concrete integers. Yet CLBZ implicitly treats a plain variable as standing only for an integer, never a compound expression. For instance, if we ask, for which x does x greater than 3 hold, then CLBZ tells us it holds for integers and only for integers between 4 and positive infinity. But we know, of course, that there are other solutions for x too, namely compound terms such as a plus b, a times b, and so on. For instance, we know that the compound term 2 plus 2 is also a solution. And to solve such problems, we use the wrapper number sign to provide a clean representation. And we also enable the monotonic execution mode of CLBZ to enforce this. So, for instance, in Scryer Prolog, we assert the fact CLBZ monotonic to enable this mode, for example, by using the standard predicate assert z, which asserts this fact. And in the monotonic execution mode, if we post is there any x for which x greater than 3 holds, we get an instantiation error, which is perfectly okay. It simply means that the argument is insufficiently instantiated to give a definitive answer, and also in this case terminate. Because clearly for completeness, Scryer Prolog would have to enumerate all terms, also compound expressions, for which this predicate holds. So in the monotonic execution mode, we must use the wrapper. So we write number sign of x greater than 3. So we make clear here that we're talking about concrete integers, not about compound expressions. And then CLBZ gives a complete answer. This holds if x is an integer greater than 3. And x can really only be an integer because the predicate in only holds for integers, not for compound expressions. So we now apply this to our program. We simply use number sign to indicate variables that we mean to stand for concrete integers, not compound expressions. So, for instance, by the task description, we mean this n here to stand for a concrete integer, and so we add the number sign wrapper. That's really all there is to it. It's a straightforward and small syntactic change to the program. Also this f here. We mean it to denote the factorial, which is an integer, and this n1 as well, and here n again. We've already indicated that it must be an integer, and it's okay to do it again here. Number sign of n. And also again, number sign of f. Then n again, and also f1. And we add a space to make this syntactically valid, and for symmetry also here. And that's all. So now, with these added number sign wrappers, our program is monotonic. And if we ask, for example, for which integers n is the factorial 2, we get the solution n is 2, and it terminates all exactly as before. And in contrast to what we had before, if we add the constraint n is the compound term 1 plus 1, then we get a type error, because a compound term is not an integer. And this is okay, because we meant the predicate to hold only for integers, not for compound expressions. And a type error, in contrast to an instantiation error, can be replaced by silent failure. So, read declaratively, this simply means that the predicate does not hold for this compound term. And our goal is, of course, to make the monotonic execution mode the default. Of course, this will take a very long time, and one may say, is this really so important? I mean, after all, for the simple things we meant to do with the program, it worked correctly. And indeed, that's true. However, what about all the other things we could have done with the program and which didn't work? We probably didn't even think of them, yet there are so many things we can now do with the program in addition to the simple things that already worked in a sense. And speaking of working, and to generalize from this specific mistake, namely incompleteness, one could say that a very common mistake by Prolog programmers is to work against reasoning. Because a decisive property of good Prolog code is that it can be reasoned about in several ways, starting from extremely basic things, such as using queries to ask the Prolog system for what holds. and also to use these queries to write test cases, and further to generalize and specialize queries and programs to find out more and to locate mistakes, or to perform various kinds of termination analysis, for example, via abstract interpretation, which can also be used for type checking and also type inference. And we can also interpret the code with different execution strategies, and so on. And all these examples of reasoning rely on properties that must be preserved. And the more properties we preserve, the more reasoning we can easily apply and automate. And if we break these properties, then reasoning becomes harder and harder, often to such an extent that we can't really apply it at all anymore, at least not easily. And we've already seen examples of desirable properties, such as commutativity of conjunction, which means that we can rely on A and B to mean the same as B and A. So we can exchange goals and therefore also automatically try different orders of goals to deduce logical consequences. Or monotonicity, which means that adding a constraint can at most yield fewer solutions, never more solutions. Another desirable property is idempotency, which means that stating a goal G once means the same as stating it several times. So with this property, we can automatically eliminate duplicated or entailed goals. Another property could be called separability. Maybe there's a better name for this, but what I mean with this is that clauses and predicates can be read and reasoned about in isolation. For example, cut violates this because it introduces dependencies between clauses of a predicate. And another property, for which I also don't have a better name at the moment, could be called accessibility. I mean that all relevant things are amenable to reasoning. So, how do we ensure these properties? Well, for commutativity and monotonicity, we already know that we must avoid certain predicates that violate these properties, such as exclamation mark, if then, not provable at this point in time, non-monotonic type tests such as integer, atom, and so on, and also metalogical predicates such as var, ground, and so on. And also, we must enable the monotonic execution mode of CLBZ, so that integer constraints are also monotonic. Then, to guarantee idempotency and separability, we must avoid certain additional predicates, most notably assert and retract, which are predicates that change the clause database at runtime. And the problem with this is that the clause database is global and implicit. So this violates separability, because other predicates may be affected by this. And in addition, asserting a clause twice also adds it multiple times to the database. So it violates idempotency too. And also, such changes to the clause database are also not undone on backtracking. And therefore, these predicates are sometimes used to imperatively express state changes. That is, where we destructively modify a state to express changes, and therefore can no longer truly reason about the change. And we call such a change a side effect of the predicate, because it's something that occurs outside the declarative meaning. Because declaratively, asserting effect simply succeeds. But it does have an effect beyond this, because it leaves an additional clause in the database, and that will affect other predicates from then on. For instance, we may have a predicate that reflects the information that an agent has found gold, say, by asserting the fact in the global database, which is a non-local effect, because we are adding a new fact, and this may also affect other predicates from now on. So we've now created a runtime dependency between predicates, because the fact found gold depends on whether P was executed or not. And when we reason about this fact in other predicates, then their meaning implicitly depends on the predicate P, even though P doesn't appear in the clause body. So if we destructively change the clause database, then we can no longer reason about predicates in isolation. And this significantly complicates testing, for example. So changing the clause database at runtime violates all these properties, and we therefore always try to avoid it. Instead, we describe changes declaratively as relations between states. For instance, in our example agent, we could have a predicate state 0 state where we relate the current state, state 0, to the next state if something holds. And depending on the situation, one of the next states could, for example, be that the agent has found gold. And now we have the advantage that we can query this predicate in all directions. We can, for example, ask, what are possible states in which we can find gold? Or, for example, which state transitions are possible at all? And we can now do this because the states are now available explicitly as Prolog terms and can now be queried and reasoned about. So this is what I mean with accessibility. We have access to the things we are interested in. They are available as Prolog terms. Whereas in contrast, if state changes are expressed as destructive modifications to the global clause database, then we cannot reason about them in this way. And as another example of this, implicit randomness is not accessible. So if we invoke a predicate to generate, for example, a random integer, and there's an implicit state that determines which integer is next, then it means that there's something in our program that escapes Prolog-based reasoning. And the program is therefore no longer entirely logical, but depends on something beside the declarative semantics. And a solution to this is to introduce an explicit seed argument. Because if the random seed is available explicitly as a Prolog term, then we can use it to reliably reproduce the outcome of our program. For instance, if we want to express a random or pseudo-random search in Prolog, then we would do this with a seed argument. And the seed can be used to initialize the random number generator. And of course, there may also be other arguments, such as a list of variables that must be labeled and so on. The point is that if we specify the same seed, then we always get the same outcome. And therefore, we can reason about the program and analyze, for example, why a test case failed and so on. So again, we've made the state accessible as a Prolog term. And as yet another example of this, consider output that only appears on the system terminal. Again, that's a side effect of predicates that write output, because declaratively they simply succeed. But as an effect, they change what you see on the terminal. And these are destructive changes, because they are not undone on backtracking. So a predicate may also write output and then fail, and yet the effect remains. And especially from beginners, we often see a Prolog predicate such as main, which is true if S is a solution to a task, and which then writes S on the terminal. And the issue here is, how do we test this predicate? Because the output only appears on the terminal, and we can't, at least not easily, reason about the output with Prolog. Of course, we could write a separate program for this, but in all honesty, who really does this? And therefore, you'll most likely not write tests for the output. So what we should have done here is to simply ask for the solution and let the top level print it. Simply post a query and the top level will automatically show the answer, as in this hypothetical example. And for more complex output, we can use the DCG non-terminal format underscore to describe the output as a string, that is a list of characters. For instance, we could introduce a non-terminal formatted solution using a DCG to describe the list. So for example, in Scryer Prolog, we load the DCGs library and format underscore is in library format. And here we state, for example, if S is a solution, then the output we want to describe is a list of characters that also contains the quoted solution S. And we call such a specification a format string, because it specifies the format of the output. And the second argument is a list with terms that are referred to in the format string. And the advantage is clear, because the output is now amenable to reasoning, and in particular to testing. So, for example, we can ask, what is the list of characters C's that is being described? And the top level automatically shows the answer. However, we see here that the string is truncated. And we'd like to tell the top level to print it fully. However, in this case, the query has succeeded deterministically, so we had no chance to interact with the top level. So we'd like to manually introduce a choice point to get this interaction. Now, how do we introduce a choice point? Certainly by introducing a choice, so for example with a disjunction. And then one may be tempted to use any predicate that first comes to mind, such as true. However, that would distort the truth of the goal, because the identity element of disjunction is not true, but false. So we can use false here. And when we post a query, we can now interact with the top level. And for example, in Scryr Prolog, we can press W to write the entire string, okay? And on backtracking, we get false, that is, there are no other solutions. And we can make this a bit shorter, like this, for example. And again, we press W here as before. And when needed, the predicate format can be used to actually write this list of characters on the terminal with the S format specifier, which stands for string. So we would first ask for the list of characters Cs, and then say we emit a list of characters, namely Cs. And so we get these characters as output on the terminal. Of course, it's suboptimal that we had to manifest the entire list in memory. So what would actually benefit most from here is a new predicate, say phrase to stream, which writes each character as it becomes known, and then immediately reclaims the memory so that the entire string need not be manifested in memory. And Prolog implementers are of course highly encouraged to provide this predicate, because then we can make more of our code amenable to reasoning and at the same time achieve good performance. In this case, especially space efficiency. And speaking about implementers, they are also prone to antipatterns, because Prolog implementers tend to draw wrong inferences about reality. For example, if constraints are slow in a system, then implementers will tend to wrongly assume that we need less general predicates too, whereas the important takeaway would be to improve the speed of constraints, for example with better interface predicates or better compilation and so on. And of course, implementers are subject to a lot of pressure, for example from publications and benchmarks about Prolog systems, which mostly measure performance, at least at the moment, up to the point that implementers tend to sacrifice correctness for performance. Because if you ask customers, do you want a fast Prolog system, then they tend to respond yes. And even if it's so fast that it yields wrong results, yes, that's okay. So customers should also think about what they actually need from a Prolog system. And personally, I think implementers are well advised to provide building blocks that let us write robust Prolog applications, starting with conformance to the Prolog ISO standard, then an efficient representation for strings, a convenient interface for attributed variables, reliable constraint solvers, and so on. Another example or consequence of wrong priorities is when implementers increase complexity instead of decreasing it. And this can happen quite quickly because Prolog programmers are quick to adopt even the greatest nonsense. And therefore, when an implementer comes up with a bad idea, then programmers often simply adopt it instead of resisting it. So popularity is no reliable indicator of quality and style. For instance, suppose I say, let's forget lists of characters and instead write characters using their ASCII codes. Then Prolog programmers, especially from Edinburgh, will adopt this easily. Or even more extremely, let's forget lists and use a new data type for list of characters. Then Prolog programmers will also adopt it. Another such idea is, for example, to say, let's make write canonical no longer emit the canonical representation of a term, but something else. Yes, of course. Or what about deviating from the standard entirely and using a different functor for lists? Perfect, right? And so on. And I'm not pulling your leg here because all these examples have actually occurred in the history of Prolog, and some of them have set Prolog systems back by many years, if not decades. Whereas a good Prolog implementer always tries to reduce complexity for application programmers. For instance, we already have many predicates and also DCGs for reasoning about lists. And therefore, strings should be lists. And to make them easily readable, they should be lists of characters, not integers. And if I want to print them canonically, then I should get the canonical representation of lists and so on. Because Prolog code should be simple and elegant, and implementers should be committed to making this efficient. So the burden should be on the implementer, not on application programmers. Another example of increasing complexity is preventing convergence of Prolog systems, because also here, implementers are quick to adopt bad ad hoc mechanisms, which only cement the differences between systems. For instance, suppose I want to make Prolog code portable between systems. So the answer is easy, right? Simply provide a way to let me detect which Prolog system is running. However, the notion of dialect is alien to the Prolog standard. The standard only knows different degrees of conformance, not different dialects. And we're of course still aiming for convergence. So we want to write our code as if there were only one Prolog system. And we don't want to make the code itself depend on any specific system. Because what if a new system comes up? Ideally, that should automatically also work, right? So we don't want to tie the application to only a subset of systems. Therefore, instead of checking for which Prolog system is running, it's better to check for features or to create separate files with system-specific definitions or to make the necessary adjustments in our system's initialization file. And then we can simply load the definitions we need. For instance, when using Scryer Prolog, we load the application code and maybe some Scryer-specific definitions. And for Sixtus, we also load the application code and maybe some Sixtus-specific definitions, and likewise for other systems. Because in this way, we are making a clear statement to implementers. We, as application programmers, will not carry the burden of plastering our code with additional checks. We are willing to tolerate maybe some additional compatibility definitions and also to provide them, but we are not making our code ugly just because the implementer has adopted bad practices. And lip service from implementers is not enough, because implementers are quick to say we should all sit together and decide on compatible features and so on. So yes, we wait for them to do it. And also, you are not only the messenger if you say, well, that's just how it is, there is this incompatibility and so on, because you are not just a messenger if you are choosing what to propagate. And you are especially not just a messenger if you personally benefit from incompatibilities between systems. For example, if you're selling or providing a framework that itself acts as a compatibility layer, right? Because then it's in your own interest to prevent convergence between systems. Or at least it has the appearance. So we wait it out instead of adopting practices that only cement the difference between systems. And in the interest of convergence, we are not testing which system is currently running. Now, from programmers and implementers on to Prolog instructors. A typical Prolog instructor may have about 10 2-hour slots to teach Prolog. Maybe a bit more, maybe even less. And Prolog instructors tend to spend a lot of the little time they have on irrelevant topics. For instance, how much of this time do you want to invest in explaining cut? And how about not only explaining it, but also complicating it? For example, what about making up our own categories of cuts, such as green cuts or red cuts, or blue or even GRU cuts? I mean, seriously, is this how we want to spend our time? With an elaborate litany of completely made up concepts? No, of course not, because our goal is to eliminate cut by providing better constructs. Or as another example, take proof trees. What are we supposed to do with a proof tree? Should we read it? So I really wonder which Prolog instructor has time to introduce an additional formalism too. A Prolog instructor should teach Prolog, and we of course want to reason about Prolog by staying close to Prolog. Because if you're using a different formalism, then who can tell whether and to what extent this actually has anything to do with the given Prolog program? And a good way to reason about Prolog code is to think in terms of generalizations and specializations, right? For instance, we can generalize away a goal. And we should make this reasoning possible. So a Prolog instructor should teach constructs that admit this reasoning. And all these antipatterns have one thing in common. They fence in the horizon. I don't mean the fence in the horizon, but they fence in the horizon. So they limit the horizon. Because the overarching commonality of all these antipatterns is that they limit what we are able to do with Prolog. And destroying logical properties is the most common antipattern, mostly by teaching outdated and problematic language constructs. Another antipattern is to not teach enough constructs. Maybe the prime example for this is to give complex list exercises without teaching DCGs, because many relations over lists are very easy to describe with DCGs, such as relating a list ls to its last element L, which holds if, and now we use a DCG to define the relation. So the list we're describing has the form ... denoting any list at all from library DCGs, and then the last element L. And if ls is of this form, namely anything at all followed by L, then the relation holds. So L is the last element of the list ls. Or as another example, relating a list ls0 to its reversal ls. We can also easily describe it with a grammar, and I leave it as a challenge. And speaking of list exercises, flatten is not a good exercise at all, even though it's often given to students, because what do we expect from the most general query, where we ask, for which lists does it hold in general? Is this a monotonic relation? And can we implement it so that it preserves monotonicity? And the name flatten is already problematic in itself because it's an imperative. And thinking about a relation imperatively already limits the generality and what we can describe with it. So limiting the horizon is also a common antipattern, and we want to do the opposite. We want to use Prolog to its fullest potential. And for this, we keep to its pure monotonic core, because in this way we can reason logically about the code and we can easily analyze it, run it with different execution strategies and so on. Now you may say, wait a minute, am I not also fencing in the horizon by advocating that only a subset of Prolog be used? So am I not also limiting what we can do with Prolog? Well, to answer this, consider the training program of an athlete. It's not enough to meticulously follow a program. That's only a necessary condition for a top athlete, because the training program itself must also be well designed and tuned. And not only that, because recovery phases are at least as important as the training, in a sense maybe even more important. And also, certain movements must be unlearned to prevent injuries or to maximize power or to increase stamina, to eliminate redundant motions. And indeed, you'll find that in many disciplines, an important factor for success is to make only the necessary moves. And if you're training hard, it may be painful, at least a bit, because it may be tough to endure, or your muscles will ache and so on. And if you train effectively, then you may consider the pain worthwhile, because you're also gaining something, such as more endurance, more power, more mental strength and so on. And there's no doubt that many worthwhile tasks are hard. For example, learning a new sport, an instrument or a language and so on can be quite hard and even painful, and also worthwhile. Yet excessive hardness of a task is no guarantee at all that the task is worth doing. Because many things that are hard are also pointless, or even counterproductive, such as, for example, learning without enough sleep and so on, or playing an instrument with a wrong technique. And I mention these examples because in the Prolog world, it's easy to waste time on pointless errands. For instance, implementers sometimes put effort into deviations from the standard, and programmers often start catering to the machine instead of talking to implementers so that the underlying system is improved for everyone at once. Or as mentioned, a lot of time is wasted on constructs that violate logical properties and so on. So these tasks may be hard, right? And they're also counterproductive, because we want to make our tasks as easy as possible so that we can do more with Prolog. And there's no need to make this harder because the challenges are already tough enough. For instance, how can we easily delegate as much as possible to the machines? How can we easily test our programs? How do we ensure that we can easily reason about our programs? What is a good minimal set of predicates for Prolog beginners? For example, do we really need the predicate format? And wouldn't it be better to provide format underscore together with phrase to stream, which is very general? And which additional language constructs are needed? For example, what about list comprehensions and so on? And we may need to delay gratification until better constructs are ready. This means that there may be programs that we can't write satisfactorily at the moment, because we don't have the right building blocks available, at least not yet. And this only means that we have to keep looking for better constructs. We hang ourselves up, like trees, because in a healthy forest, the young trees don't get much light, and therefore they grow slowly, and therefore the wood becomes strong. And we accept nothing but the best. So we truly want the best constructs, not the hardest or most painful ones. Writing elegant programs should be easy as possible. And finally, maybe the strangest antipattern of all, namely regressing. Because I've seen a few Prolog programmers, not very many, but still at least one or two, who very quickly learned many things and then regressed. In the sense that they'd suddenly start recommending constructs that an experienced Prolog programmer will try to get away from, because they are too hard to use and reason about. And I don't know why such a regression happens. Maybe they internally try to justify it with Prolog is not a purely declarative language and therefore we can use imperative constructs. But the reality is that Prolog has a pure monotonic core. And we automatically get all desirable declarative properties as long as we keep to this core. And it's one thing to slip and occasionally maybe use a construct that destroys these properties. That's comparable to an athlete who falls and then immediately gets up again. But it's a completely different thing, and this is what happened here, to start running into an entirely wrong direction. And what's strange in addition to this is that the regressed users are often also the loudest. So they even advocate the regression. And we must decide now, should we try to outscream them? And personally, I think no, because our task is to prepare a free Prolog system that has all desirable properties, guarantees and features, with the goal to run the Prolog teaching environment Gupo in a free Prolog system. Because Gupo will make the relevant arguments for us. Because Gupo, first of all, enforces the pure core, and second, shows what is possible, for example, termination analysis and so on, if we keep to the pure core. And importantly, Gupo makes Prolog education scalable, because we can run it for hundreds and thousands of students at the same time. So, to prevent regression, keep in mind that the power of Prolog is rooted in the logical properties we ensure. And if we violate them, then we can no longer depend on them. And then the core attractions of Prolog are lost.